Hi guys, in this video I'll walk you through one of the key components of the kernel or key processors of the kernel, which is process management. So I believe the last few classes we looked at the different responsibilities of a kernel. We discussed the responsibility of the kernel to manage its devices, and under that we looked at the direct memory access controller and how it sends data to peripherals. And today we're going to start off by looking at process management, which is one of the most crucial and lengthily discussed sections in your syllabus. Let's start. Process management. Now, the first question you need to answer is, under process management, what on earth is a process? Now, a process is defined as a set of instructions that are being executed. It's a set of instructions or program that is being executed. That's a process, so that's simple enough. And when executed, the time that the process has control of the CPU is known as its burst time. So we're learning about a new term here. Basically, a process, of course, has to go to the CPU to get executed, right? But the idea is, when that process enters the CPU, the process will take over that CPU for a given amount of time. So that time duration, the time duration that the process takes charge of the CPU while it's being executed, is called the processor's burst time. So for example, a process that has a burst time of, let's say, 2 milliseconds would occupy the CPU for 2 milliseconds, and that's all. A process that occupies the CPU for 5 milliseconds would be given a burst time of 5 milliseconds, right? So I've said the same thing the other way. The idea is, the burst time is basically the amount of time a process has control of the CPU, because as soon as the process enters the CPU, that process has control of the CPU for that duration. Now, for a process to run, it needs data. The data required for a process to run is contained in a data structure known as the process control block, or PCB. Basically, a PCB is a data structure that is associated to each process, which basically describes to the processor what on earth this process is, what its current state is, what is it going to do, and a lot of other information, right? So generally, a PCB or a process control block is a data structure that contains the data required by a processor in order for it to run it. All right. The PCB has the following structure. Now, the structure of a PCB is not that important, but let's quickly discuss it. The process control block, or PCB, has something called the process pointer, which is basically a small address that tells the processor where that process exists in RAM. And then there is something called the process state. Now we will discuss what the process state is in detail soon, but there are three possible states a process can be in. It could be ready, it could be running, or it could be blocked. Next is the process ID, which is a unique ID assigned to each process to make sure that one process can be identified from another. Next up, something called process priority. Basically, there are lots of processors that are competing for the attention of the CPU. However, the CPU selects which process to process depending on its priority, meaning if a process is more important or is of higher priority than another, it will process that first. So we are looking at something similar to what we discussed under interrupts. Remember something called interrupt priority? Similarly, we also have something called process priority, which dictates the priority level of the process. Then process privileges. What resources a process can access? Can this process access the RAM? Can this process access the printer? Can this process access files in the hard drive? What sort of privileges it has? And then the process register values will also be stored in the process control block. Now, when that process was running, there would have been an associated program counter value, an associated memory address register value, memory data register value, accumulator value. Now, those values would be retained in the process control block. So the idea is, when a process is running, the data of those registers would be stored in the processor, but for some reason sometimes these processors might need to be retained in order to be accessed later. Remember the concept of interrupts? We learned that the process needs to be restored back after an interrupt is serviced, right? Where does it restore the process back from? Now we know that it restores it back from the process control block, because the process control block is what contains the associated processors PC, MAR, MDR, ACC values. So if a process can't take place now, the data would be stored in the PCB so that it can be retrieved later. And finally, the process burst time, which is basically how much time the process would occupy the CPU. Right, that's the process control block and sort of things you would have inside the PCB. Now, we're learning about the process state, which is very important. The idea is the process state is the state of a process requiring execution. Now, that isn't very explanatory. What exactly does that mean? There could be three states that a process is currently occupying. The first state is ready. This is a process that is waiting for the CPU. The second state is running, the process that is currently running in the CPU. And last but not least, blocked. Blocked means the process was previously running, but it was momentarily paused since it is currently waiting for something to happen. And usually this is either some user event or input-output operation. So the idea is, guys, the CPU would take in a process. However, it will be in one of three states while it's being executed. While it's waiting to get a chance to go to the CPU, it's in the ready state. But once it finishes executing, of course, no problem. While it's executing, it will be in the running state. And last but not least, once it is running, but sometimes it is still waiting for another IO operation or an event, maybe something from the direct memory access controller, for example, it's waiting for the DMA to respond. Something of that sort, the process will be blocked, right? So three states: either it's waiting for the CPU, aka ready, it is running in the CPU, aka running, and it is blocked by the CPU, which is to say that it is currently waiting for an IO operation or event to occur to continue. Right, that's clear. What did we look at all this time? What is process management? What is a process? What are the three different process states and the process control blocks components? Next up, we have something called the process state diagram. Now, this is very important. The three states we described earlier are described very diagrammatically in this diagram. Let's understand. We'll start off understanding this diagram from the top left. This block or this circle denotes a particular state that this processor is currently in, or this process is currently in. And you might remember these or recall these diagrams when we discussed finite state machines or state transition diagrams in AES level, right? It's pretty similar to that. So the idea is we start from the top left. This demarcates, the new circle demarcates the new process, that is a new process that is coming to the CPU, right? And this process, that is a new process, wouldn't initially just be taken into the CPU. It will be admitted to something called the ready queue, guys. So the CPU doesn't just take in any process that comes along. The CPU has connected to it something called a ready queue. A ready queue, which I'll denote as RQ. And it is to the RQ that new processors will come. So the queue will get full like this. And when the CPU is ready, it will sort of fetch one process from this ready queue one at a time. So remember, new processors, although we learned like this a few lessons before, remember new processors don't just end up in the CPU at once. They are taken in by the ready queue, and it is from the ready queue that the CPU takes one process at a time. Right. So the first task is a new process is initially admitted to a ready queue, which is basically a queue that contains the processes that are ready to be executed by the CPU. So what you can understand from this is, can you all maybe guess processors in the ready queue? What might be its process state? it should be in the ready state, right? Because they are now ready to be executed, right? Then what will happen is the queue, or not really the queue, but more precisely, the processor would pick a process from the queue, right? And what happens when that happens is the process goes from the ready state to the running state. And I want to clarify one small thing. I told you that a processor picks a process from the ready queue, right? That's not so true. The processor has an accompanying sort of assistant called the scheduler, and the scheduler's job is to select the process that the processor should run. So it's basically like this. You can think of the processor like the manager and the scheduler like the manager's assistant. If there is someone that's trying to see the manager, the assistant would provide an appointment for this employee or person to meet the manager. So the manager wouldn't be directly talking to the employees or any person that's trying to talk to him. The assistant would provide a sort of schedule to when these incoming people should visit the manager, and it is out of these schedules that the assistant would pick the correct person and send to the manager. So the idea here is the processor has the ready queue, but from the ready queue, the scheduler picks the next process and sends it to the processor, and it will run. Okay, fine, no problem. So we are done discussing this point, we are done discussing this point. Now, once the process finishes running, the good news is it will finish, right? It will finish, it will then exit the queue, right? It doesn't have to go back to the queue, it will just exit. No problem there. But sometimes a process might execute, but it might need to be executed again. So it's like an employee trying to visit a manager, and yeah, he has an appointment with the manager, he talks to the manager, but then the manager says, come back again at this time. So then he'll have to be on the schedule again. So in this case, in a computer's case, the process goes to the CPU, does whatever the hell it has to do, but it ends up back on the ready queue for some future processing. And when that happens, we call that an interrupt. From running state to ready state, you call an interrupt. So we looked at few state changes. New to ready, it's when it's admitted to the ready queue. When the scheduler selects a process to run, it's the processor's state changes from ready to running. Of course, when the process finishes running, it will be exited. But if the process needs to be processed further later, it will switch back from running to ready. And the last state we discuss is the blocked state, which is what happens when it's waiting for something to happen. So what will happen is the process would currently be running, but the process would be blocked. It will be waiting for some IO operation to take place. And so it will be in the block state until then. And then if it enters a block state, guys, it wouldn't immediately go back to the CPU again. Right? What will happen is it will go to the block state, it will wait for the IO operation to take place. Once the IO operation finishes, it goes back to the ready queue, because there might have been a few other processes that require more urgent execution that came after the blocked process. So they need to be attended to before the blocked process is taken again. So yeah, the process was initially running. For some reason it became blocked, but then it doesn't go back immediately to run. It will go back to the ready queue and wait for the CPU to call it back again. Right, so that's how those states change. We'll discuss those state changes in proper full form here. When a process goes from new to ready, we call that the admit phase of the CPU. What does that mean? A new process is placed on the ready queue by the high level scheduler. Okay, we're looking at a new name called a scheduler, and it's apparently a high level scheduler. Let me read that again. A new process is placed on the ready queue by a high level scheduler. And there's an important point here. Until CPU time is allotted to it. What does that mean? So the idea is, what that last underlined statement means is, it will stay in the ready queue until the CPU gives it time to execute. Okay, right. So a new process is placed on the ready queue by the high level scheduler. And we don't know what the high level scheduler is, but you probably understand what a scheduler is. A scheduler is an assistant to the CPU, another program actually, that picks someone from the ready queue and places it in the CPU. But that is the scheduler, right? And let me precisely mention that what I described earlier is not just any scheduler, it's a low level scheduler. So there are two schedulers, guys. Earlier we just looked at it as scheduler, but now we have something called high level and low level scheduler both. So what are the differences? The low level scheduler, which I'll demarcate as LL scheduler, low level scheduler, is the one that picks a process from the ready queue and sends it to the CPU. So it picks from the ready queue and sends it to the CPU. Then high level scheduler, HL scheduler, his job is to pick incoming processors and put them in the ready queue. So new processors to ready queue. Do you guys understand how these two work together then? So the high level scheduler picks an incoming process, like maybe let's say you turned on a Chrome tab. The Chrome tab process is picked from the processors and placed in the ready queue, right? That's done by the high level scheduler. And then once the CPU is ready, the ready queue process, that is the Google Chrome process that is currently in the ready queue, is sent to the CPU by the low level scheduler. So process enters the ready queue via the high level scheduler. The process exits the ready queue into the CPU via the low level scheduler. So there are two different schedulers, one to put processors to the ready queue, other to take processors from the ready queue to the CPU, right? Hopefully that makes sense to you, right? Fine. So that's the admission phase of any process where a new process is placed in the ready queue by a high level scheduler. Next up, we have the ready to running or dispatch phase. Basically, what does this mean? The process is going from the ready phase to the running phase. So it's now finally entering the CPU. Let's see how that works. In this phase, what happens? The process is taken from the ready queue and is allotted CPU time by the low level scheduler so that it can be executed. So that's pretty straightforward, right? A process is picked from the ready queue and sent to the CPU, and who does this? The low level scheduler. Its responsibility is to pick processors from the ready queue to the CPU, and that's that. That's called dispatching. And then running to ready, we call this interrupt. Let's see what that means. Once a process is executed during its time slice, an interrupt occurs and the program is moved back to the ready queue. So the idea is sometimes processors don't execute and finish off. They might need further time. So remember I told you each process has something called a burst time, that is how much time that process is allocated to the CPU. That is called the time slice here, right? Same thing, burst time. So we are saying, okay, this process is given, let's say 5 milliseconds of burst time. But that is like the only time it is given for that appointment rather. If the process wants more time, it will have to go back to the ready queue and come back at a later time. So that's what this means. So an interrupt is sent, which means what happens here? The currently running process exhausts all the time that is allocated to it. So it goes back to the ready queue and comes back when it has more time available, right? So that's running to ready, called interrupt. Then what happens if if the process goes from running state to block state? We call that the event wait process. What happens here when a process goes from when a process goes from running to blocked? What happens is the process needs to carry out an IO operation. So the operating system scheduler places the process into a blocked queue. Okay, we are learning about a new queue here. We learn about ready queue, but now we have something called blocked queue. So the idea is when a process is doing a task, sometimes the process might require a further IO operation or event to take place. So when that happens, remember how I told you it will be given a blocked state, but then there might be multiple blocked processors right now. There's not just one blocked process at any given time. There might be multiple blocked processors. So what happens is, just like the ready queue for ready processors, there's a blocked queue for blocked processors. So if a processor needs some event to take place before it can be further executed, it will be sent to the blocked queue in this event wait process. So what will happen here is the process will go from running state to block state, which is where the scheduler places the process into a blocked queue. Then finally, once that process is happily ever after, once it receives the event that it was waiting for, the process returns to the ready queue once the IO resource is available. So that's when the process changes from blocked to ready state. We call that the event phase. And finally, once the process finishes, it exits. The processors finish executing. That's the release state. So these are all the states of the processor described in 6 different words. Admit is the first phase from new to ready state. Then ready to running is dispatch phase. Running to ready is interrupt phase. Running to blocked is event wait phase. It's waiting for something to happen. Blocked to ready is back in the ready queue. That's the event phase when an event actually occurs. And finally, it exits, which is the release phase. There you go, guys. That's all there is to the wonderful process life cycle in a CPU. Right, amazing. Okay, so that's good. In this video, the last thing we'll look at is something called round-robin scheduling. Now, before we look at the term scheduling or what the hell round-robin means, let's just focus on this diagram, because this diagram will help us reinforce what we learned earlier. This is the CPU, right? Notice the CPU has multiple arrows coming into it and coming out of it, right? The first arrow is this dispatch arrow, which has a ready queue. This is what I was talking about all this time. So look at this, guys. There's a high level scheduler which will take in an incoming process. Let's say that you now opened a new game on your computer. The game's process will get admitted to the ready queue and it will sort of end up on the ready queue. And then once the CPU is ready, the low level scheduler will dispatch a process which probably will be a game process from the ready queue to the CPU. Once the CPU finishes executing it, it will release it back. But let's say for some reason the CPU needs to execute it further later. What will happen? The CPU will send it back along this arrow to the ready queue. So it will end back on the ready queue, waiting for further time to execute. That's when you have an interrupt. Otherwise, the process might be waiting for an IO operation. Let's say that you're playing the game and the game is waiting for you to press the up arrow key. Then you're waiting for an event wait phase. So it will enter another queue called the blocked queue, which is also that picking and placing in the block queue is done by the low level scheduler. It will get placed in the block queue, and finally, once the event occurs, once you finally press the up arrow key, it will end up back on the ready queue. So these are all the processes described very neatly on this diagram. So the idea is this overall process of taking a process, giving it some time and executing it, that overall process is called round robin scheduling, guys. Round robin scheduling. So the idea is round robin is a scheduling algorithm that uses time slicers assigned to each process, and all processors have equal priority. So a round robin basically means you have a process, each process is given the same time. The process either executes in that time and finishes off, or if it can't finish it off in that time, it will go back to the ready queue and wait for it to get more time. That's round robin scheduling. So it's a very a sort of a very democratic process where each incoming process will get equivalent amount of time and have equal priority to execute in the CPU. Right. So there are a few terms associated here. Each process, that the time that each process gets is called time quantum. So the time that the CPU allocates for each process is a constant in round robin scheduling. That time is called time quantum. This time could be anywhere from 10 milliseconds to 100 milliseconds. That's all. Then finally, when the time quantum ends, The low level scheduler puts the process back into the ready queue. So it might need more time or it might release itself, but if it needs more time, it will end back in the ready queue. When the time quantum ends, the status of each process is saved so that it can be restored when it's allocated in the next quantum. This is very important, guys. Now, let's say that there's a process here. That process is executing in the CPU. But let's say that its time quantum is over. It was given 10 milliseconds, nothing more, but it couldn't finish in 10 milliseconds. It'll go back to the ready queue. But then the thing is, the CPU should know what was the last execution that was done to this process, right? Because it can't start from the beginning. It needs to remember what was done to it last. The status of this process before it exhausted its time quantum should be saved somewhere. Sort of like saving its progress so it can be used or it can be executed from the point it stopped. And that process of restoring is where the PCB comes into play. Remember the process control block? Basically, once a particular process exhausts its time quantum, the time it is allocated, the contents of the CPU registers that were associated with that process is saved to that individual processor's process control block. So it's all like a directory that says, okay, this is all you did in this time quantum. Let's call that T1. Let's say there's a process coming in at this time quantum T1. It couldn't finish it in time quantum 1, but it can't start doing the process again in the next time quantum if it was given more time. It'll have to start from wherever it was previously stopped. So what will happen? Once a process finishes executing in that time period, the processor will save that processor's associated data in that processor's PCB, process control block. So when the process is given more time at another time, what will happen is the processor can read that processor's PCB and resume continuing the work that it needs to do. So it's not starting from scratch. Basically, a process finishes because it exhausted its time quantum. That processor's data from the CPU is saved in the process control block, and then it is read back again when the next time quantum is awarded to it by this processor. Right, guys, so that's about it for how scheduling works, specifically round robin scheduling. In the next few videos, we'll look at how the processor multitasks, how the high level schedule and the low level schedule are different with specific details, and finally look at process priority and have a sneak peek at scheduling routine algorithms. All right, that's it from today or for this video, guys. I'll see you in the next one. Bye bye.